All right, let's start it now. So, oxidation reaction. The oxidation reaction, if a compound has a double bond, right? If a compound has a double bond, you can use two different methods in general. One is the bromination reaction, where the color of the bromine decolorizes. Whereas on top of that one, if you have an alkene double bond and you use the potassium permanganate solution, an aqueous solution of potassium permanganate, the purple color of the potassium permanganate was now converted into the manganese dioxide. And manganese dioxide is a black color, right? At the same time, the double bond, across the double bond, you will insert the hydroxy group into that. And this type of a dihydroxylated compound, 1,2-diol compounds are known as glycol. Okay? And I can go over the mechanism of this one, and mechanism is a little bit tricky, but I don't want you guys to know the mechanism, right? But just for your, so what's going to happen is that you have a potassium permanganate has a manganese, right? And dioxide like this, right? So like this. So this oxygen goes here, this double bond attacks here, and it goes like this. And it's from a cyclic molecule. Remember, cyclic molecule, right? That's cyclic molecule, and then further, in presence of the water, right? That water will get rid of this manganese, and then water, and then potassium hydroxide, which is water and potassium hydroxide will form the potassium hydroxide, and then the manganese dioxide will be also released. So basically, it forms the transition state something like this. Let me show you the structure of oxygen, manganese, and manganese, right? Like this type of structure. So I don't want you guys to know this type of this oxygen also goes here minus. Hold on, this is wrong. Minus here. Because this type of a transition state comes, right? And then with the presence of the water attacks here, and this one goes this, and another water comes here, and this goes this way, right? And then basically it is cleaving off here, and we put the hydrogen here to get the glycol. Okay? So this is how the mechanism works, but I don't want you guys to know the mechanism. Next reaction is the ozonolysis. Ozonolysis is basically an ozone. It is cleaving the double bond. Okay, if you have a double bond like this, right, all you need to do is just cut this molecule into half, right, exactly half, and put one oxygen here and one oxygen here. Done. See? One oxygen, another oxygen. So likewise, this is with the zinc and hydrogen, right? First of all, it forms the ozone reacts with the double bond to form the molybdenite, okay? That molybdenite gets reduced by the zinc to form the aldehyde. If this is the case, aldehyde and ketone. So because remember that this R means, let's suppose that if it's the CH3, this CH3 and this CH3, then you'll end up getting acetone, right? Which is a ketone, right? Now depending upon what kind of a groups are here. Now if this is a CH3, so the CH3 will be CH3, right? CH3, COC. Now this will be what? Ketone, right? The name of this compound is acetaldehyde. It's called acetaldehyde, depending upon what kind of a group. Two methyl groups, right? Is a ketone. One methyl group and one hydrogen is an acetaldehyde. Okay, with presence of zinc hydrogen. But in contrary to that one, if you use the ozone at the first, right, it forms the molybdenite, and with the hydrogen peroxide, the whatever thing like a ketone will remain ketone, right? But the aldehyde will further undergo the oxidation into the carboxylic acid. So basically, there are two different types of reactions in the ozonolysis, right? In this reaction, ozone and zinc will form ketone and aldehyde, right? Or ketone and ketone, or aldehyde and aldehyde. Whereas in the case of the ozone with hydrogen peroxide, ketone remains ketone, but if there is an aldehyde, that aldehyde will change into the carboxylic acid. Okay? So if you take a look at the mechanism of this molecule is something like this. First of all, it forms the alkene forms the molybdenite, and then converts into ozonide, and this ozonide gets reduced by the zinc and acid zinc, as acid water and zinc, right? It gives it either aldehydes or ketones. Okay, so that's what it is. Now, instead of a zinc and hydrogen, the water is there. Instead of a ketone, then it's ketone, but if it's an aldehyde, aldehyde will further oxidize into the carboxylic acid. So overall, this mechanism is like this. Do you need to know this mechanism? No, you don't need to know this mechanism. I don't want you guys to know it. Okay, but at least try to know the structure. What is the name of this guy? And see what's going to happen, right? But most important thing is ozone cleaves the double bond, which is, you know that now. What is the role of the zinc versus hydrogen peroxide? That will be the main question in the examinations also. Okay? Any question about ozonolysis? The ozonolysis, you know, the ozonolysis will, so remember that the ozonolysis, in the ozonolysis, ozone will cleave this double bond, right? Basically, right? And it forms, look, if the oxygen, if you incorporate oxygen here, this is the ketone, right? If you incorporate oxygen here, this is the aldehyde. That's what you got it, right? That remains as such in the case of the zinc and hydrogen. But if you have an ozone and then followed by the hydrogen peroxide, it will cleave ketone. That ketone remains ketone. It doesn't do anything with the ketone. But if it's the aldehyde side, that aldehyde will be converted into carboxyl. Make sense? Nisha? So now we come to the, after this, we come to another reaction. It's called the radical addition of the double bond. Okay. So why we're talking here all of a sudden now, it's a radical addition polymers. So now when we talk about the ethene molecules, right? So that ethene is a double bond containing molecule, right? Alkene. Is that alkene? This is the alkene. So when alkene and alkene comes together, it forms a long chain carbon. Okay? And that's what is called now the polyethylene. So it is a bag that we use, a polythene bag, right? That's what is the polythene that is generally manufactured starting from the alkene, as for example, ethylene. This ethylene undergoes a radical reaction. And in the radical reaction, generally there are three steps which we already studied: initiation reaction, propagation reaction, and termination reaction. Remember in the halogenation reaction of the alkene. Right? I believe it's the chapter number 2 of it, right? And at the end of the chapter number 2, we studied about the radical reaction. In this reaction, we use the peroxide, right? That peroxide with the heat or light, right? Will homolytically cleave. If there is a two electron is shared by the two oxygen, and oxygen have an electron here, right? So this is the initiator now. This is called the radical initiator. What the radical initiator does is undergoes a radical propagation step, where there is one is the sigma bond and another is the pi bond, right? Pi bond also has two electrons. So one electron will go and react with the OR, right? Another electron will go to the CS2. So it forms another radical. This radical further reacts with another molecule in the same way, right? It goes this way and it's formed a chain and then it elongates and so on and so forth. This is how it forms a long chain polymers of ethylene. That's what we call the polyethylene. Okay? This type of reaction is called the radical reaction or radical polymerization reaction. Okay? So whenever we have a radical reaction, that radical reaction does not only just ends up into a long carbon chain, right? It may end up like a branch or circle or so depending upon like a type of the reason. People have studied so much about this, they can easily manipulate the rate of the reaction and the outcome of the chemical product. Okay? They can get the linear polyethylene, you can get the branched polyethylene, and so on and so forth. And it's all cool. They also know at what time they need to stop the reaction. If they stop the reaction, they know what is the length and how much you can make it out of that. Okay? Okay, any question about this one? This is polyethylene. It's a very, very simple one, right? And remember that this is the polyethylene, right? Let's see, this is the polyethylene, right? Polyethylene, ethylene is this guy. And you have a propylene, right? This propylene will give the polypropylene. And if you have styrene, right? This is the styrene. This styrene will polymerize to give you polystyrene. So remember that you have this flat, right? This is polystyrene, right? This is the polystyrene, right? So likewise, polypropylene tubes. The polypropylene tubes are the homes of polypropylene tubes, right? So those are all made out of this polymerization reaction. Okay. Right. So with that being said, now we move on to the another one now. Okay. So let me a little recap it before I go on to, because it might get overwhelming for you guys, right? Before I do anything. So what we studied in the double bond, okay? We studied in the double bond the halogenation reaction, right? Hydrohalogenation reaction, right? And then after that we studied what? Hydration reaction, right? While talking about the hydrohalogenation reaction and hydration reaction, we studied about the Markovnikov rule, right? And after that, we studied the hydroboration reaction. Hydroboration reaction produces anti-Markovnikov product. That's what you need to understand, right? Markovnikov product is produced by the hydrohalogenation reaction and hydration reaction. That's what you need to understand, right? Hydroboration reaction will give you anti-Markovnikov product, right? Now, another reaction that we studied is hydroxylation reaction, potassium permanganate. If there is a double bond in the molecule, if you add the potassium permanganate, you will add 2 OH groups across the double bond, right? Across the double bond. And these OH groups always come from the same side, right? From the same side. That's why this type of addition is also known as syn addition, right? And in the case of the hydrogenation reaction, another is a hydrogenation reaction where we talk about a double bond and we added the hydrogen across the double bond, right? But that is also 2 hydrogen is coming from the same side, right? So that is also another syn addition, okay? And we talk about the polymerization reaction. Now we'll extend the same conjugated reaction of a hydrohalogenation in terms of compound having more than one double bond. As for example, this type of a system, okay? So this type of a system is called a 1, 2, 3, 4. Excuse me. So remember that there is a double bond, there is a single bond, there is a double bond. So whenever this type of a system is present, what kind of a double bond is this? Is this a conjugated double bond? Is this the cumulative double bond, or is this the isolated double bond? This is the conjugated, as per you can see the title of the slide, right? Conjugated system. Conjugated system means what? You have a double bond, single bond, and double bond. As you can see that double bond, single bond, double bond, right? So now we provide the HBr. If you provide the HBr, there is a 2 typical things possibly happens, right? In this reaction, if you have a HBr, the double bond attacks to the hydrogen, we know that, according to the Markovnikov rule, and then hydrogen will go to the carbon having a higher number of hydrogen, right? Take a look at the hydrogen carbon number 1 and carbon number 2. This is the 2 hydrogen, this is the 1 hydrogen. So 2 hydrogen, right? That means this carbon number 1 has a 2 hydrogen. So hydrogen will go to the carbon number 1. And bromine will go to the carbon number 2. Now you might want to say that, why it is so? Why not 1? Why not 4? Right? Yeah, it's also possible. It's the same thing, right? This molecule is a symmetrical molecule. You can number it from here. 1, 2, 3, 4. Front side and back side. Both ways it is the same carbon, right? I'm seeing the double bond resides across the carbon atom and at the same position, right? So there's no changes between the top nomenclature versus bottom numbering, right? It's the same thing. So even though hydrogen goes to the 4th carbon and bromine goes to 3rd carbon, you'll end up getting the same product, right? Actually, it's not a similar, it's the same product again. Now, besides that, whenever there is a conjugated system, the conjugated system not only undergoes addition at the carbon number 1 and carbon number 2, right? So 1 and 2 is called 1,2 addition, right? Now, this type of a compound may undergo addition into, and then it can resonate while adding the main bromide, and then if that is the case, you will end up getting 1,4 additions. So let me show you one thing. So let me do that. Okay. So now, if I have hydrogen and bromine here, now remember that double bond has to attack the proton and bromine has to leave. If that is the case, now remember, according to the Markovnikov rule, hydrogen will always stick with the carbon having higher number of hydrogen. So instead of a 2, now this carbon will become 3, and you will have a positive charge in this carbon and CH and CS2. Now, see the system here. What kind of system is this? Positive, single bond, double bond. This type of system is called conjugated system, right? Still a conjugated system. So the pi one bond is a sigma bond, now there is a pi. Pi bond is a mobile bond, right? So this mobile bond now can flip over here. As it flips over here, you'll end up getting CS3, C, H, double bond, carbon, H, double bond, C, oops, excuse me, single bond there. CS2 here, right? And there's this guy. And with that being said, now what's going to happen? This bond moves here, so the positive charge will reside into the terminal carbon. Now you can see that CS3, CS3, CS, CS, double bond, CS, CS. Now there is a CS2. Whatever is left, bromide is left as an ion. So that will come and attack here. This product. Right? So exactly same thing is happening here in this mechanism, in your book also. So double bond attacks the carbocation. Once the carbocation is formed, it splits the pi system and it forms the resonance. So it goes to and fro. That's why you have a resonance has a double-headed arrow. See that? Go forward and backward. It will go this one, okay? Both ways. Now, in the next one, what's going to happen? If the bromide attacks the 4th carbon only gives you this compound. If the bromide attacks the 2nd carbon, right? Bromide attacks before it undergoes this resonance, right? It will end up giving you 1,2 product. So this is called 1,2 product. This is called 1,4 product. Any questions? Okay, good. Now, in this reaction, in this problem, it has shown that there is a structure, right? There's a structure here, and there's a double bond, and then positive charge. So what it's asking here is resonance hybrid structure. First of all, you need to draw the resonating structure. What is the resonating structure of this molecule, right? How the resonating structure works? Because remember that pi bond is a mobile, right? It can undergo delocalization. So you have a positive, single bond, double bond, always undergoes this resonance. Okay? So for this one, this bond may flip this side. If that is the case, what's going to happen? We'll end up getting double bond comes here, positive charge comes here, right? So now, for this positive charge is here, positive charge, single bond, double bond. Again, in order to neutralize this positive charge, double bond has to come this way. If that is the case, again it goes back. So these two are the resonating structure of this molecule. So generally, hybrid means it's not the true structure of any of these ones. It is the structure in between them. So basically, the electronic cloud is all the way from this carbon to this carbon. And the positive charge is hovering around the carbon number 1, carbon number 2, and carbon number 3. Right? That's what it is, the resonance hybrid structure. Now, if you draw the structure like this, right, that is wrong. That is not correct. Because the positive charge is just between 1 carbon, 2 carbon, and 3 carbon. Right? So you just make a dotted line and then put the plus sign. Okay? All right. 1,3-butadiene. This actually is the same thing what we just did. Okay? This question and answer, right? Expected product of the 1,2 addition and 1,2 word. It's the same thing that we just studied. Okay? See, 1,3-butadiene, right? Just asking the 1,3-butadiene, same thing. Okay? All right. Any other question? Now, I would like to just introduce one small thing here. I think I already talked about that. The double bond having another additional carbon and positive charge, right? This system is called what? Allylic system, right? This type of carbocation is called allyl. Remember that what did I say? Double bond and next carbon. This carbon is called allylic carbon. This hydrogen is called allylic hydrogen, right? And if there is a positive charge here, suppose this hydrogen is gone, right? If the hydrogen is lost, and this cation is now called allylic cation, right? This allylic cations always undergo this resonance. So see, positive charge, single bond, double bond, right? So it always undergoes this resonance. Okay? So same fact is here, also same thing, right? Double bond, single bond, positive charge, allylic system. See that? This system is the allylic system. Okay? Now let's see another example here. For example, I believe that you do not have this one in your book, maybe. I don't know. Okay? So now let's see this one. In this case also, we are just having this type of a compound. And you have a bromide here, right? It's Br. In this case, the HBr, the Br will attack. If I write it down correctly, it's supposed to be like this. The double bond has to attack from this way. The double bond will not attack. Why? Because it has a CS2, right? That's what it is. So it again depends upon. It also depends upon what type of temperature and what type of condition is that, right? And equivalency of the molecules. But anyway, in general, if it's a kinetically controlled reaction, then the double bond will attack the proton and bromine will leave. After leaving that, remember that it follows the Markovnikov, and you have a secondary carbocation. What did I say earlier? Carbocation is a bad dude. What does it do? It tends to steal, or it tends to stabilizes, right? One way is the metal shift, another is the hydride shift, another is the resonance, right? So this system is also allylic system. Remember that. Positive charge here, single bond here, double bond here, right? So now if this bromide, right, attacks this carbocation before the double bond comes here, then we'll end up getting 1,2 addition. Right? Now, in addition to that, if there is a chance the bromide is coming slowly, right, and the double bond has a chance of flipping this side before the bromine attacks, then you'll get the tertiary carbocation, right? This carbocation is definitely more stable than the secondary carbocation, right? So, if this is the case, then what's going to happen? the bond will slip this side, and bromine will have a chance to attack the more stable side, and it gives you 1,4 product. So now you can see that there's a important thing. One is the secondary, one is the allylic resonance, right? This is the resonance. The another is the secondary carbocation versus tertiary carbocation, right? So which one is stable? The tertiary carbocation is stable, right? So definitely if there is a mixture, then you will end up getting this as the major product, right? Again, it also depends upon the temperature. If you lower the temperature significantly, the resonance will be stopped, okay? Resonance will become sluggish, right? It will happen very rapidly. So bromine has a more chance of attaching to the secondary carbocation. Although it's a secondary, because due to the low temperature, right? At the low temperature, resonance will not happen fast, right? So this would be the major product in the low temperature, whereas this would be the major product in the room temperature and high temperature. Yes. Okay. Any questions about now? This one. Okay, good. Now, if I ask you this question, what's going to happen in exam? Right? This is also possible. Double bond, single bond, double bond. In this case also, same thing will happen. See? Forget about this part, right? Forget about this part. You need to worry about these double bonds also, right? So your product will be, you try it at your home, okay? Your product will be 1,2 versus 1,4. 1,2 product will be something like this, 1,2 product. And 1,4 product will be, try this. Okay? Hydrogen here, and here. Makes sense, right? So this is the 1,4 product. Try the way that I did it here and in the previous slide. Right? So try the mechanism a little bit and then see whether you will get the 1,2 and 1,4 product or not. And make sure that you will get it. Okay? So in addition to that one, do another reaction also. Put methyl group here, right? And do the same reaction. What are the products you will get? Try it. Okay? Alright. So if you don't have this question, now I'll move on to the next question, which is called the cycloaddition reaction. In the cycloaddition reaction, the diene and dienophile reacts to give cyclic molecules. What is that? This is called diene. You know that, right? Carbon number 1, carbon number 2, carbon number 3, carbon number 4. We just studied that one. See that? Read the same compound like this, it'll be like this, right? Diene. Right? 1,3-butadiene. And we know that this is the ethylene molecule, right? This ethylene molecule and then butadiene, it comes together, we'll just heat it up. What's going to happen? It just condenses, right? This double bond flips here, this bond goes here, and this bond goes here. So basically, a bond will be formed between this carbon and this carbon. And it forms something like this, right? So this type of addition is the cycloaddition reaction, okay? And this reaction is a very easy and very fast reaction, okay? And it's a very, very stereoselective one, okay? Now, what did I just say here? This doesn't make sense to you guys, right? So let's see this one. So if you have a double bond like this, right? Double bond, right? And if I have an alkene like this, right? So basically what's going on here is, this alkene is attacking this carbon. This bond is flipping here to make a double bond. And this double bond is attacking another carbon. right? So as a result of which you'll end up getting this type of structure. Right? And you have double bond is forming and double bond is forming here. So this type of structure you're getting. So new bond is forming, the old bond is breaking, right? The old bond is pi bonds, and there is also a new bond is also forming. So basically with that, you'll end up getting double bond like this, right? Cyclohexane, 6 carbon, 1, 2, 3, 4, 5, 6, right? 6 carbon. So this type of a dienes, right, can be of a different type. See this diene, this is also diene, this is also diene, right? So you can try the same reaction. You can, whatever you did it with the double bond, you can just take this molecule, right, and you have the double bond here, right, and you put the double bond at the bottom, right? This is diene, this is dienophile. So what's going to happen in this case? This double bond will attack this carbon. This bond flips. This bond is attacking this carbon. Right? With that being said, now what's going to happen? In this case, right? I can put it this way, right? And then what I can say? There's a bond is formed between, there's a 2 carbon here, right? 1 carbon, 2 carbon. I'll just put it 1 carbon, 2 carbon. And one is form a bond here, right? And they are another from here. So this is the bicyclic system, right? So the bicyclic system, you can write down the same compound in this fashion also. See? Same thing, right? Bicyclo 222 octane, right? And so you can try with all these 3, the double bond. And the diene, so like the dienes are the varieties of the diene, there's the different varieties of dienophiles. These are the dienophiles. Okay? What is the alkene? A double bond containing one, only one double bond containing a mark, right? Carbon-carbon double bond. These are called the dienophile, like the alkene over here, right? So in this case, this group acts as a reactive site, okay? In each of these cases. Let me see this. Okay. So now, let's see a few examples. You have a diene and dienophile. It undergoes a cycloaddition reaction. So suppose this is the diene and this is dienophile, right? What's going to happen now? So basically, this reaction happened in this single step. So I'll just read out this structure. This is the diene, right? And the dienophile. This dienophile, this is the dienophile, right? This is the dienophile. Let's see that. And one of the dienophile is this guy, right? So this dienophile, now whenever it comes and react with this dienophile, this whole group, this carboxylate group, right, the ester group, goes underneath the compound. So basically what I'm trying to say here is CH3CO this has to, if I draw this a little bit clearly, you understand very, very precisely. That's why I just wanted to make it a little bit nicer and bigger and nicer. So you have this compound. Okay? So now I'm going to put this group underneath, right? So C is 3O2C. Makes sense, right? And then we have a double bond, and same thing. C is 3O2C. So this is what it is, right? So if I have this one, right? So this group, remember that this group goes inside that pi system. This pi system actually helps to stabilize these groups. Okay, so that's how it loves to stack. The pi stacking is called the pi stacks. It's like a sandwich, making a sandwich. So during this process, this double bond attack here, this goes this way, and this double bond attack here. It happens in the one single step. So one more time, if I try to draw the transition state here, the transition state would be something like this. Hold on, right? Like this. And this carbon has a, remember that, I'll just write it down, Me for CS3, okay? CS2, right? Carbon. And also there is a MEO2C, the carbon, right? So that's what's going to happen here. With that being said, now what's the next thing happens? After it forms the main bond, the bond will go here, right? And this type of structure is formed, and this whole group, this COOMe and COOMe, both of them lies underneath like this, COOMe, right? And hydrogen will stick it up, and will stick it up. So because there is a hydrogen here too, right? I didn't go down the hydrogen here. So now, if you take a look at this molecule from the top, right? What's going to happen? You'll end up getting OH at the back side, right? Now, if you take a look at the molecule from the bottom side, what's going to happen? These two groups will be in the front, right? Which is this guy, right? So this compound, you can write it this way. The product, you can write it this way, or you can write the compound in this way too. CO2, CS3. But only thing that you need to know is that they have to come from the same side. If one is sticking downward, the other should also downward. If one is sticking upward, another should also stick upward. Do you understand this? This is a little bit tough for you guys. If you understand this, this is a really, really, really good. Okay. Now, let's try to understand another reaction so that you'll have a more clear vision. Okay. Let me first of all take a look at another molecule, and then I'll say, see, now in this molecule, it's the same thing, right? It's the same thing. Again, you have double bond here, and remember that in this case, there is a double bond, right? And one is facing CO2, CS3 is facing outside. The another one is facing inside, right? CO2, CS3. Remember that. So there is a sacrifice. If one goes inside, the another has to stick it outside, right? So now if that is the case, this bond will go here, this bond hits here, and this bond goes here. So what's going to happen now? In this case, we'll end up getting double bond will form here. Now for this OH group, it will be outside, right? CO2CS3, right? Whereas for the one at the behind underneath, what's going to happen? It goes like this, right? CO2CS3, right? So that structure, this is structure, right? If you take a look at the molecule from the top face, you'll end up getting this one, right? You can also draw the opposite conformation. You can also draw, if you take a look at this molecule from the bottom side, you will see another structure, which is this structure. CO2, CS3, and then CO2 and CS3. Right? So there are two double bonds, right? This two double bond will flip it here. And there's a 3 pi system. Remember that there's a 3 pi system. 1 pi, 2 pi, and 3 pi, right? So out of these 3 pi will convert into 2 sigma bond and 1 pi bond. So that's what it is here, right? So there's a new sigma bond and new pi bond. Does it make sense? There's no cis or trans. This compound is a trans. This is cis. The top one is a cis. The bottom one is trans. Okay. Okay. So you can see that this reaction is a one-step concerted reaction. This is called concerted reaction. Okay. And it happens at the one time. Either it comes from the bottom phase, it comes from the top phase. I don't want to get it too much complex. This is already too complex for you guys, right? So Let's not do too much complex here. Okay? So these two examples are, because I can go and then talk about each one of these examples. We already talked about this middle one. Okay? So now, if you try to do this one, this will be interesting too. So what it says that how can you make this compound? How can you make this compound? Simply by Diels-Alder reaction, right? So all you need to see is that you need to break the bond here, right? If you break the bond here, you end up getting one side here and another side here, right? And just to make sure that you just do another cycloaddition reaction. Bond goes this way, it goes this way, it goes this way, you'll end up getting this, right? There will be one sigma bond, one pi bond, and one new pi, two sigma bond, and one new pi bond, right? That's what it is. Limonene, don't do this one. This one is a little bit tough for you guys. But I mean, this one should be, you guys should supposed to do this. Okay? So for this one also, again, you have diene and dienophile. I'll do it to one of them, right? The top one, which is a little bit harder. So you have a furan molecule. This molecule is called. Not good. I'm just writing here. It's so difficult. So you have a furan here, right? Furan this way, right? And you have a diene. See, this is a diene. This is a dienophile. So dienophile is what? Double bond, right? And cyanide, right? Cyanide is CN. So CN has a triple bond. Remember that, right? This triple bond. So this triple bond has a pi system also. So it goes underneath the compound, right? So that's what it is. So now what's going to happen? This double bond will attack this carbon, this double bond flip, and this double bond attacks this carbon, right? So as a result of which, you end up getting transition state something like this. Oxygen here, carbon, carbon. And you have another bond here, right? Bond here. And you have a cyanide here. Remember that cyanide, CN. CN is inside and hydrogen is outside. Hydrogen and hydrogen here, right? So you have a bond and another bond is there, right? So this is structure. You can write it this way now. Look. I put the oxygen on the top. This is the furan molecule, right? And the double bond will be a new double bond will form here, right? So new double bond, I put it here, right? And there is another stuff from where? From the dienophile, right? And you have a hydrogen here, hydrogen here, and you have a cyanide at the bottom, right? So this is the structure of the molecule. Okay? Any question? So try this compound and this compound. These compounds are relatively easier than whatever I have drawn. Do you guys understand this or not? Diels-Alder reaction will be in question exam as well as in the quiz. So remember that. Okay, that's a very good question, Teresa. So let me do it. Which one is for that? That's a good question. Let's do it one more time, okay? One more time, and then you guys understand that. Okay. So let me rewrite this structure, right? This is the furan molecule, which is the same molecule. So now you have a double bond, right? And remember that whenever there is any system which has a pi bond, like carbon, triple bond nitrogen, if you go back to the slide, you'll see this. This has a pi system. See that? Pi bond. This has a pi here. This is a pi here. This is a pi here. This is a pi here. Right? They all go down. So except this guy. This side is a linear molecule, so it has two different structures. Okay? So we're not going to deal with this guy. So let's see all these groups, right? These groups. Look. One more time. This group. This group. This group. This group, as well as the one at the bottom. This group and this group. They all go inside the structure. Inside the pi system. There is a pi system on the diene, and there is a system in the dienophile also, right? So they just stack it on top of each other. Okay? So this double bond You go and attack here. This double bond comes here. This double bond attacks here. Right? So as a result of which, you see that oxygen is here, right? And you have double bond is formed here, and you have a hydrogen and cyanide at the bottom, hydrogen and hydrogen at the bottom. You can see that there's a hydrogen here too, right? Because hydrogen is by default, you don't need to draw it, right? You don't need to draw the hydrogen here also, right? But in order to assign the cyanide, you have to draw the hydrogen at least at this side. Any question? This is hard. This is really hard, right? And if I were in front of you, I would have explained you much better. But this is what it is. I mean, from the online system, because I can show you the models and then talk about the different. It's coming from top face and bottom face. But overall, this is a difficult thing. Okay, you guys practice it, and then you slowly understand. Okay, first of all, you need to go back and try this yourself a couple of times, 1 time, 2 times, and try all these examples to understand. Because I put the stereochemistry here. The stereochemistry makes everything different. This one also, you can draw the stereochemistry of this molecule also. Okay. I think once you have a practice, we'll get it. Yeah, I think you need to practice it. No matter how much I talk the same thing again and again and again and again, it doesn't. It feels like, oh, you understand. I understand now, right? And you try to draw it, you don't understand it. So you got to go back and see whatever I said, right? And then you try it again. So step by step, do it slowly, step by step. Once you have one of them correctly, you will have everything correct. Okay, I bet you that one. Okay. All right. So what's the time now? 2:52. Okay, I'll stop it right here. So.